Good morning, everyone. So I'm happy to be here to present some of my projects. I do research on IoT and IoT security. So I thought I would talk about multiple projects rather than just one project going into deep, and give you some vision on what's going on with IoT security. So let's start with the IoT. What's happening in IoT right now. And I think IoT acronym is now accepted by everyone, Internet of Things. And we all know that this is referring to the smart devices that have computation, communication, and sensing capability. And we are using them in our homes, for instance, right? So we have these devices, smart watches, smart meters. And indeed, there are 6 billion IoT devices used worldwide. This is 2020 number from Gartner. And there are many applications already utilizing IoT technologies. These are very critical applications: transportation, smart health, agriculture, energy, smart city, etc. So it's already happening. And when we look at back a little bit, the research with the IoT, there is this IoT device, and when you put the IoT devices together, you have the IoT network. There's an infrastructure that is formed, and typically now they refer it as a 3-layer infrastructure where you have IoT devices at the bottom, which is called the perception layer, and of course the network layer to communicate the data coming from the sensors, and then storing data on cloud and managing it and analyzing it, etc. On the left side is the IoT device itself. So the device has obviously software and hardware components. So there had been a lot of research on the hardware side since this research started in early 2000. So the people focused on building energy efficient memory, CPU, radio, etc. So it is by itself a subdomain. And then there was a lot of research on the wireless communication aspect of these IoT devices to communicate with each other or communicate with the infrastructure. And then obviously the security and software related research, a lot of things on security that we will talk on the cloud side, obviously, and the data analytics research. When you collect data, tons of data from IoT devices, and you can analyze them on the cloud and make a decision based on this data. So when you look at the 20 years of IoT research, I think this started early 2000 with sensor networks. So I was a graduate student at that time, and the name IoT was not there. And we had these tiny sensors, and people were talking about sensor networks. And then, as time passed, after I think 2010, they started to use IoT, and it is now the common name. But when we look at the research here, as I mentioned in the previous slide, there's been a lot of research. So from hardware to communication, software, security, data analytics, a lot of advancements have been made, both in theory and practice. And we now have even standards or products. So when you look at these communication standards like Zigbee, LoRa, these are all developed after that, research started with sensor networks. And now today they are standards, right? So we have products using them. Or, we have these programming platforms with IoT devices and Android, iOS and Raspberry Pis, right? And there's a lot of, again, security and privacy standards that are used today from IEEE, and a lot of machine learning, AI-based edge processing and data analytics. So this has already been done, and I think most of the fundamental questions have been answered. So just wanted to show you that after that 20 years, So this is currently what we have in terms of the spending on IoT. So when you look at the different applications here, depending on the area, we have a lot of investment in US dollars. Of course, this is from 2020 latest. These are 2020 and the blue ones are 2015. And you see there's a quadruple increase in the spending, and this is going on. So it's a mature area now. So that takes us this issue then. So when you work on IoT, if most of the fundamental problems are already studied and addressed, so what is left, right? So I think we're at the second level maturity for IoT, that now there are products, there are applications, people are using them. So as researchers, what can we do? And I believe that we are at a level where we can bring IoT to masses, because now there are a lot of IoT devices that you can use them in a lot of applications, and you bring into laymen. So even people that are not knowledgeable about IoT devices can use them in daily life applications like health, agriculture, transportation, etc. So what does that mean? It means we are moving towards more application-oriented research. So there will be a lot of research trends on the application side. So what does that mean? Now you will focus more on the engineering challenges, right? So you have IoT devices, you have some solutions, you put them together and build a system. Or there will be interdisciplinary challenges, because now the IoT applications will be on different domains, different disciplines, right? And those disciplines may have their own challenges or restrictions that you need to work with them. Or you need to deal with scalability and interoperability. This is the interoperability is the key word. There's a lot of products from different companies. They cannot talk to each other. This is a big issue when you talk to people in industry. So from our perspective, perhaps it's not a research issue, but when it comes to the design and engineering, the interoperability should be there, and you need to come up with really efficient solutions to address that. And finally, management challenges. So when you have these IoT devices and networks, you need to maintain them. You need to manage them. Like if something happens, you need to deal with that. So it's like network management. This is similar to IT research when it started early 2000. Everybody has these IT systems, and then suddenly they needed IT people to manage their networks, right? So now we're at that level where we need people to manage the network, device, and security, and we need researchers to come up with efficient solutions to do that for us. So what I will talk about today is some management-related research that we are doing at FIU. There will be 3 projects, and I will go a little faster given the time, but I just want to give the idea and what's going on, and if there is any interest in certain details, we can, of course, discuss offline. So I'll start with the security management. I mentioned management is an issue for IoT, right? And security is a big part of it. We have like these critical infrastructures which deploy a lot of IoT devices like smart grids, smart cities, right? And you would like to collect data. You have thousands of devices perhaps, and obviously you will provide security, right? So when you provide security, there are solutions. So you can use those standard encryption algorithms or authentication algorithms, etc. So it exists there, but the challenge here is how do you manage this at scale, and how do you manage this with the resources available? So for instance, let's consider the symmetric key management problem. So symmetric key is a shared key that you want to use between 2 devices or a device and a server to encrypt the communication, right? So we want to have scalability there. Like when you have large number of those devices, how do you manage the computation and communication overhead? So the computation is mostly about this lightweight cryptography. So there's a lot of research already going on with lightweight cryptography. This is for cryptography researchers. They already studied this and they came up with solutions. But the communication part still needs some additional solutions, because in some cases, not, of course, this is application specific, you may have IoT communications that are not really supporting large bandwidth. So we may be talking about bandwidth of kilobits per second, right? So for instance, if you look at legacy technologies like 2, 3G or power line communications, or even you look at the current IoT communication standards like Bluetooth, Zigbee, LoRa, these are providing data rates in the order of kilobits. So what does that mean when you would like to come up with a key management scheme at scale? Then there will be a lot of messages going back and forth, and they will eat up your bandwidth. So there will be less room for regular data communication. This is a challenge. So you have this restricted bandwidth, and you would like to come up with message-efficient key agreement and renewal. So one use case for this is the smart grid, as I mentioned. There are a lot of IoT devices and a lot of standards already available for smart grid, and they have security solutions as well. You see these standards listed here. And still they have a problem. The problem is this was a project with Department of Energy, so we work with a real utility company. And what they asked us is, well, they said we have a low bandwidth radio communication for our field communication. So there are field devices, and they are spanning tens of miles, and they are talking to a control center, but the bandwidth is very low. So what they are doing is they're transferring data. Now, when you're transferring data, you need to, let's say, change the data every time you make a transfer. This is for good security practice, right? So if you do that, then it will create a lot of overhead, additional overhead, because the bandwidth is already limited. So what they told us that, well, they don't change the keys. The symmetric keys need to be updated frequently. So they don't change it for a year because of this problem. And that's a security risk, right? So we want to make sure that they change. This is something called perfect forward secrecy. So we decided to tackle this problem. And obviously, the symmetric key exchange problem is not a new problem. So it has been studied in the past, and there are already solutions. So when you look at even our internet solutions, like TLS, you use it every day, right? Transport layer security is there based on Diffie-Hellman. And this is an example of how it happens. So there's client server, and they exchange these client and server hello messages. And then they authenticate each other. They also create a key that they can read by using Diffie-Hellman approach. These are well known. When you look at the overhead of them, you see you need to spend 2 RTT. This means 2 round trip time. 2 messages will go back and forth, right? That's called RTT in their overhead measure. And if you look at, for instance, this IKE standard or TLS 1.2, this is the former version, they have 2 RTT. And there's now TLS 1.3, which came 2018. This is the latest version. It's 1.5 RTT. So still, this is efficient, but not enough for that bandwidth that I was talking about. And the reason is that because these solutions are all designed for internet, right? And so they never thought that, well, let's design something for smart grid or design something for low bandwidth environment. So what we did is we designed a new key management protocol for smart grid applications like this, like with low bandwidth communications. And the idea here is Diffie-Hellman is still there. And we use it with a concept called hash chaining from cryptography. And we are able to achieve 0 RTT. So in the first message that you're sending, you are able to create the key and start encryption, right? And this is also secure, there's authentication, and there's replay attack resistance. So this is the first replay attack resistance, 0 RTT key exchange mechanism that we propose in the literature. And as I said, this was a Department of Energy supported project, so we applied for a patent. It's pending, almost there. it will come in a couple months. So how does that work? Just quickly, this is Diffie-Hellman, and I don't know if some of you may be familiar with it, but it's difficult to get into the details here. The basic idea is user A and B, they exchange some public keys, and they have their own generated random keys, and eventually by this they can agree on the same key. This is Diffie-Hellman, basic Diffie-Hellman, right? So what we do is we use Diffie-Hellman, and for key agreement, we have our own setup and configuration phase, and we have a key renewal phase in our approach. And this is I think the main idea here is that the control center is talking to field devices. So there are, as I mentioned, there are many field devices, and they send data to a control center. So initially what we did is we give each of them a chain. I mentioned that this is a hash chain-based approach. So this chain is a hash of a number, a random number, n times. So you're getting the hash n times, and that creates a hash chain. So you see when you apply the hash n times, you will get something like this, and then you can dissolve it, right, one by one. So you give it to every device, or for every device, we create this hash chain based on a nonce, a random nonce. And we also give them a public key from the control center for each device I. So this is the setup phase. They are given in advance. And we put an update time here. So that gives flexibility to the application designers that whenever we consume n, or whenever they want to update this public key parameter, you can adjust this, right? So if you want to update quickly, you can make this a short amount of time, or you can just rely on n, and can be picked very large that it might be usable for 1 month. So what happens then in the protocol is that you see this is the IoT device initiating the conversation. So the control center already sent it to this yi, and it generates a random number, and by using yi, it can find the key, that Diffie-Hellman key. So that key is used here for encryption. So you see in the first message, we have the key, and we are encrypting. But also, we are sending a parameter, this x, to control center so that it can also generate the same key. So it is generating it here, the same key. The nice thing here is this checking of the status. So this is from client to control center, right? So when the control center receives this message, it will have this chain, SIN. So it can verify that, I have the same chain, they have the same chain, so that means it's coming from this device, so it is authenticating, and it's also preventing any replay attacks, right? And the server also does the same thing, so it now it replies because it now has the key, so it can encrypt as well, but it's sending the next portion of the chain, so SN-1 here. So what does this mean now? They update this. It's like keeping states. So you're updating the states each time, and here, when this the IoT device gets this number, then it can check it by getting another hash. So when you get the hash of n-1, you get n, right? So it can verify it. So this way, it will continue until you consume n. But this is like keeping the states, and you can do authentication. You can prevent replay attacks because you know those numbers, right? And the key renewal is done by, if you want to change this key, then you change the random number. So each time you have a new random number, and now that means it's a new key. So this protocol was done by using TCP. So these messages are going back and forth, we make sure that it's reliable, so they're not lost. So if you use TCP, you don't lose them. But how about if you use UDP? If you use UDP, the nice thing is it's faster. So TCP will require additional message exchanges, right? So if you use UDP, then there's no reliability. So what we did is, since UDP is attractive in terms of even becoming faster, we introduced an application layer protocol that will take care of that reliability. So if there's anything lost, so we introduce a sequence number, retransmission count. Basically what TCP does in a micro scale was done here. Right? So this way we were able to use UDP as well. And actually that provided us really good performance. I'll show you. So for evaluation, we wanted to test this, and we decided to use LoRa, because LoRa has this very limited bandwidth, right? So we created a testbed with LoRa, and we also tested with a simulator because we want to see how it behaves when you increase the number of nodes. And then we compared it with TLS and DTLS approach. So TLS is the TCP version. DTLS is the UDP version of TLS, right? And what we compare is the completion time of the key agreement process. So you send that message and you have the key, and that's the time where you have the key, so you record it. So the first one, the LoRa testbed, we had Raspberry Pis and dongles and created a LoRa gateway. So we created the setup of FIU campus, and we connected to a Things network. LoRa has a Things network, and it is further connected to cloud, Amazon Cloud. So now we can send messages from here to the server, and we can test our approach. For simulation, we created an S3-based environment with Linux containers that for field device and server, but we bridged them with an S3 network devices so that we can get this LoRa communication simulation available to us. And we use different settings. So for instance, in urban areas, we used 200 field devices in 1 kilometer per meter. That was for rural, it's 10 kilometer per meter. And we generated some background traffic. So when you are doing the key renewal, the data traffic might be going on, right? So we need to generate some background traffic, and we did that with these different options. So here are some testbed results here. There were two options to run, TLS and DTLS. So either you can start with PKI, public key infrastructure, or even public shared key setting. So here is the PKI results, and our results is these two, right? The orange ones. So UDP, you see, is much better compared to the others in urban and rural settings. And same for PS key assumption. But for PKI, we're even saving much more. So for instance, it's like 45 to 60 seconds in TLS, DTLS versus less than 15 seconds for our approach. And then for simulation, we verified that the behavior is same, and with background traffic, even we can improve the gain. So you see in the worst case, we reduced the time by 4 times with UDP approach. So you see the UDP is much better compared to TCP. So this is still going on. We are extending this work with more experiments and more UDP details. So it's being submitted to a journal. Now the second project I will talk about is about 5G security. So there is this 5G device-to-device communication. Probably you may have heard about it. And this is used in device-to-device or vehicle-to V2X, in short, communications. So in this way, you can involve IoT devices to 5G. So 5G is not just becoming, bringing improvements in terms of speed, bandwidth, coverage, etc., but it's also there's a significant effort there for integration of IoT devices. So that's one of the major components of 5G. And they have this 5G proximity services, PROC. This also exists in 4G. This is the standard offering the device-to-device communication protocols. And when you have the IoT devices, that's my focus at least, right? So when you have the IoT devices within the 5G network, then you're basically increasing the attack surface because now these are unattended devices and they can be captured, compromised easily, and then you can have denial of service attacks, impersonation, malware, etc. So also, when you have large number of them, the issue is, again, management of security. So you have large number of IoT devices. They all need to deal with authentication, certificates, etc. And this traffic is coming to 5G core. So some background here for PROC, 5G PROC. This is defining two types of D2D communication. One is direct discovery, so it's like ad hoc mode. But the other one is the PROC UE to network relay. So there is a network relay that they pick, and this network relay is connected to the 5G network. And the others don't have connection, but they have connection to this relay. And so this part, these are called remote UEs, and 3GPP standards is the 3GPP. They have all the standards for 5G. They have a section on both of them describing how this communication happens. So for this, these are under release 16. So when we check the release 16, they explain how it happens, but they don't have anything for security yet. Like how do you ensure the security of the communication here and up to the 5G core, right? So that's probably coming in release 17 or later, but for now there's no standard, there's no solution. So that's why we focus on that part, and we said, well, we need an authentication protocol from those remote UEs to access the 5G core functions, because otherwise you may have malicious remote UEs, or you may have replay attacks. Somebody can sniff that communication and replace it and connects to the network, right? So because of this, we wanted to offer an authentication solution. And what we did is we went back and looked at 4G PROC, because that already exists and they have security solution as well. So in 4G, their solution is based on the assumption that the remote UEs will be communicating some core functions like this AAAS or PROC function. These are functions that are sitting in 4G core. And that means that each time you want to authenticate yourself, then you need to go through that 5G connection, right? So it's something like this. So let's say this guy would like to communicate to access 5G network, then it will through the relay, but the authentication happens through these, of course, it's through first this serving network, AMF, and then now these core network functions are responsible to generate material and to authenticate these devices. This is in 4G, right? So we are thinking that if 5G also follows a similar idea, then it will be a similar context. I mean, the network functions will probably change name, and there may be more network functions, but again, it will require these messages, 8 messages back and forth here. So if you consider millions of IoT devices, we're arguing that this is going to introduce a lot of management traffic, right? Authentication, keys created, coming back, etc. So what we wanted to offer was, okay, why not handle this job at this UE network relay? So can we just talk to UE network relay, get authenticated, get the key, and start the data session? So in order to do that, you need to basically delegate resources and authority to this guy, right, in advance. So it's like you say you give resources to the relay and you just give authority on behalf of the core network. And this way it can do everything, like including authentication. So we borrow this proxy-based signature concept from cryptography. It's a delegation-based approach. So it's like, you know, so when you are voting, sometimes, you know, you're absent and you give somebody proxy, right? So it's similar here. So this proxy signature, this is in general how it works. Let's say node A would like to designate node B as its proxy so that it can sign on behalf of node A, right? So it will send some delegation parameters, and then node B will generate a signature on behalf of A, and then sign with that signature and send it to this node C. So node C now knows that it's coming from node A actually, but it was signed by node B, so it's like a proxy here. So we apply this idea, and we wanted to do the same for the relay. So this was a joint project with the Idaho National Labs, and the scenario we considered was public safety with drones, and that's why, you know, I will describe it based on drones. So there are two phases here: delegation and discovery and authentication. So the first delegation phase is where you provision the material. So you give the leader drone all the material for creating a signature. Of course, you need to register all the drones through 5G registration services. And then what happens is there is this discovery process in Pro-C. So in discovery, if you're a leader, you're saying, hey, I'm here. I'm looking for remote UV devices to connect through me, right? So you're sending a message, and if there are people around, then they reply. So in that discovery, what we proposed was, okay, during that discovery, why not send a signature, proxy signature? When you broadcast that message, it's like, this is coming from the 5G core, right? So that proxy signature is indicating that this is really coming from 5G core, and these drones can verify it, and then they can also send a message. Even they can send a proxy signature so that this can be a mutual. So it's not like this guy is authenticating to these remote UEs, they also authenticate. So it's a mutual authentication. So this is the protocol based on model A and B. This is from the standard. So if you consider model A, for instance, it will leader announces itself, and then so we follow the same messages. We got the same messages from 4G Pro-C, and we basically revised those messages to ensure that proxy-based signature. So this is the details of how you generate the proxy. It's a lot of cryptography here. Basically, it's coming from the core function AAAS. It's the server responsible for it, and it gives these material to each drone, including the leader drone. So it basically generates the RI and SI and a warrant, and these are called delegation parameters, and they are sent to each of these nodes. So the server initially at the delegation phase will send these RI, SI, or RL, SL for the leader. This is the warrant, and this is the public key of the AAAS function. So the public key is should also be there, indicating that this is coming from that function. And then for verification, then for generating of signature, then this leader node will generate a proxy. Will generate a proxy key pair based on this formula. These are from cryptography again. And then create a signature using that private key, and sign something like a timestamp and broadcast it to everybody. So then they will be able to verify it, and this is how it works based on the use proxy signature. There are many proxy signatures. We used one of them, and they differ based on the parameters that they use. So we also tested this just to see how this reduces the number of messages and how much time it saves to us. So NS3 has a 5G module now, and there is also an implementation of 4G proxy in NS3. It's a GitHub, available on GitHub openly. So what we did was to look at the number of messages. So this is the LTE or 4G proxy security solution. This is our solution. And you see that the number of transmission and reception. So we are almost reducing the number of messages 5 times. And this translates to time, right? So when you look at the communication delay for our approach, it's 635 milliseconds, almost double for 4G based solution. And the only overhead here is the computation delay coming from the creation of the proxy signature. So when you add it even, it will be 836, and still we have around 33% faster than proxy solution. So what we do here now is we want to implement this obviously in a open 5G core implementations. There are many challenges in the integration of these approaches with the current 3GPP standards. And we would like to look at other cases, direct communications, TLS-based approaches. And there is also a patent pending for this, and we're also submitting a journal version of this work. So the last project I will talk about is a different one, IoT with cryptocurrencies. So maybe you have heard about cryptocurrencies. These are very popular now with Bitcoin especially, right? There are tons of them. And it was mainly because of Bitcoin, which was introduced in 2009, and this changed everything because it offered an architecture called blockchain. It's a data structure. So the Bitcoin is based on this blockchain, right, which is secure and it's immutable, so you cannot delete it, you cannot change it, you can just append to it, right? So based on that, we have lots of coins, see Bitcoin and Ethereum, but Bitcoin is the widely used one because its market cap is still 50%. There are probably 6,000 cryptocurrencies, and Bitcoin still has 50% of the market cap. So a lot of people use this, and they would like to use this in micropayments. Like let's say you go to Starbucks and you want to pay with Bitcoin, right? It's like $3. That's not possible right now because the transaction validation time is long in Bitcoin. It takes maybe more than an hour. And you need to still pay a transaction fee, which is expensive. So you may pay more than the coffee, right? So that's why what they want to do is they want to come up with solutions that will make Bitcoin accessible for micropayments. And one of this solution is a Lightning network. So as the name suggests, the Lightning network makes Bitcoin faster. So it's on top of the Bitcoin. So it's like a second layer. And on this layer, you're creating a network. So this is a payment channel network. And it's much faster. And I think there are more than 10,000 users right now. So it uses this off-chain concept. It means you're not writing everything to blockchain. You're just writing certain things like this. For instance, when you would like to talk to someone, do transaction with somebody, then you're not writing every transaction on the channel. But what you do is you open channel, and as long as the channel is open, you can make transactions. And these transactions here are called off-chain. So we're not recording them. What we record is channel opening and channel closing, right? So this way, it's much faster because now it doesn't require proof of work here, etc., right? So this gives us really instant transactions with Bitcoin on Lightning network. And that takes us to IoT. Now, remember I said I want to pay with my phone for my coffee, right? So now you can use actually a Lightning network to do that, right? So you can pay Bitcoin through Lightning network, and there's no third-party intervention. It's more secure. So this might be a viable solution or attractive solution for IoT devices, right? But there are challenges here. So the main challenge is that in order to run Bitcoin and Lightning Network, you need to install a lot of software. So you don't have enough storage and computation, obviously. So you cannot really use them directly. So you need to have a computer to do that, right? So that's why we came up with a solution that will enable an IoT device to make a Bitcoin payment without storing the Bitcoin. So this is referred to as machine-to-machine economy or crypto economy. So this is a growing trend here. You have a lot of IoT devices, and remember, in the past, they were sharing data. Now they want to do transactions among each other. So for instance, you're parking, right? So you park and you don't pay it with your phone. The car will pay it for you, right? Or you have toll payments. Maybe it's a better example. Your car is charged through the RFIDs, right? And it's between them, so you don't do anything. Or you can sell data, sensor data, and these can be done between the IoT devices. You don't need to get involved. So this is a growing trend, and it's coming. So it's called machine-to-machine economy, and we wanted to contribute to this machine-to-machine economy. So this is our solution to use Lightning Network. You have your IoT device, and you want to make a payment to this node, which is part of the Lightning Network. So everything here, blue, is Lightning Network, right? So what we do is, the only thing that you need to do is you pick a gateway in the cloud, and it will act, again, as a proxy, on your behalf to make your payment. That's the idea. But since you cannot trust this gateway, we are using something called threshold cryptography. And this way, we'll be able to just have our IoT device send a message to the gateway. That's it. And the gateway will take care of it. So how does this happen? Through threshold cryptography, as I mentioned. So this is the cryptography that deal with distributed operations. More than one party is involved. For instance, you have a key. The key is divided into multiple pieces and shared among the parties. So it's like a password is divided into pieces, and there are 5 people there holding each piece. So if they want to use the password, they need to come together and they enter those pieces, right? So it's same here. If you want to create a signature, then 2 people should come together and create a signature. So here in this case, 2 people is IoT device and the gateway. So they use this threshold signing from this reference that we work. This is actually a company that contributed to this work. And these are our threat model where we don't trust the gateway, and because the gateway can steal funds from the IoT, and it can collude with the other LN nodes. So we're looking at those collusion attacks and stealing the funds. And what we did is basically there are 3 steps we modified with LN: channel opening, channel closing, and the payment. So we introduced our own channel opening and payment sending and closing in this paper. It was published last semester. So basically what we did is, okay, if you want to open a channel for an IoT device. So the IoT device does not have anything, right? So it cannot access Bitcoin. It cannot access the blockchain. So what it does is just knows this gateway. The gateway is doing the transactions, right? So if these red ones are already happening with LN, Lightning Network, what we introduce is these messages, the green ones, so that the gateway can talk to the the IoT can talk to the gateway and can order it to sign a transaction. So the main thing here is this step 8, threshold signing for bridge commitment transaction. So basically, the LN gateway is opening a channel on behalf of the IoT device and getting funds from a wallet, putting it there, right? That's IoT device's money. But if you want to open this channel with the bridge LN node, then you need to get the signature of the IoT device as well. So it's an integrated signature with IoT device and LN gate through this threshold cryptography. So what we introduced here as well is a service fee. So why does the gateway do this, right? I mean, there needs to be some incentive. So gateway will charge some transaction fee. So we put that in the commitment transaction. So it's we introduce another output. This is a common commitment transaction in Bitcoin. So you know, if you have this 10 Bitcoins, then 10% of it will be charged by the gateway when it's forwarding it to this node. We also added that. And the sending is similar. So now you open the channel, you can talk to the bridge node, and you can send a transaction. Again, you are signing it with threshold signatures because it's a integrated signature. Closing is done in two ways. So either the gateway can close it mutually or unilateral. So the gateway, after closing the channel, will need to let the IoT device know about it. So here we did some analysis on the security of this. And I think this part, the collusion attack part, is a little interesting because we're using game theory there. The gateway and the bridge LN node can collude. So here there is a sequential game analysis. This is the options, and we're showing that the equilibrium is that the gateway closes the channel normally, so it doesn't try to announce a revoke state broadcast. So it's like you can you can announce a revoke state, means you're trying to fake the bridge node and get the money by showing that actually the previous transaction amount is there. So we show that this is not possible, and the equilibrium is the closing the channel normally, and the others are more natural. So the IoT device and LN gateway collusion might happen, but in this case, if the bridge is online, then it can recognize this and punish them. This is the feature of LN. But if it's offline, then this is a general lighting network issue, so there's no solution for it. And the IoT device and the bridge cannot collude because they don't know each other. The bridge is selected by the gateway. So we did implementation of this. Actually, it was an interesting implementation experience because we work with this guy from Zengo. So they have this threshold cryptography code, and we implemented it. The Raspberry Pi, a Linux machine, basically wanted to make a payment, a transaction through the Raspberry Pi, and it goes to a server. So we use the Wi-Fi, and we use this Bitcoin version, and we looked at the delays. So how much does it take to get a transaction? So this is compared to the case where we don't have IoT. Like there's the gateway, it sends a transaction. So there's no IoT in the picture, right? So if that's the case, then the payment sending time is 1.4 seconds. Right? Channel opening, channel closing, we don't look at them because these are done in advance, right? So it's not impacting our payments. So for the IoT case, the transaction takes more time. Why? Because they need to agree on this signature threshold cryptography runs among the IoT device and gateway. That's why we get this introduced overhead there. But still, it's 4 seconds. So it may be viable for some applications like toll, for instance. So we tested this on a toll case. So basically the idea is, so your car is passing through the toll, and let's assume that it's paying through Wi-Fi in this case. Might be Bluetooth or something else too, right? So if you assume the speed of the car is 80 miles per hour, And if you assume this transmission coverage, 250 meters between the toll and the car, right? Then you're basically having around 7 seconds because the car approaches and then leaves and then now loses connection with the toll, right? So that's 7 seconds. In 7 seconds, you need to make sure that the transaction is done, right? So if you look at the previous result, it was around 4 seconds. So with this assumption, we can't pay the toll on time. Of course, this is based on Wi-Fi, right? So you're testing it with Bluetooth now, probably will be more. And we'll see what should be the speed in order to make it happen. And there's cost analysis here. So if your gateway charges 5%, and you use it 2 times a day, so monthly will be $2.25 compared to your credit card. In some cases, you have fees, right? So it's not it's negligible. So there is a company interested in using this in parking app in California. We're in talk with them. So finally, I would like to wrap up with some of the projects that are going on that I couldn't talk here, and if there's interest, we can discuss. So there is a cryptocurrency forensics project. This is about the cryptocurrencies that I just mentioned. So you can use them on your phone, and if there's an investigation on your phone to find out which cryptocurrencies you use, which transactions were happened there, etc. So that's a digital forensics project. There's a center at FIU that we work with. There's a lot of research going on with Lightning Network. This is we're doing privacy analysis, and there is a lot going on with 5G security, as I mentioned, with IDEO National Labs, and there's big interest in testing the security standards, whether they are really secure or not. There is a SDN, software-defined networking-based project for automated vehicles, NSF project. There's a newly funded NSA project. Again, this is based on SDN-based network defense. There's a lot of training programs as well. We do a lot of cybersecurity education at all levels at FIU because we are a minority institution. But there are also training for public sector. This is an NSF project for us. We're training local governments. With Cisco, we are doing IoT in hospitality because in South Florida, this is important. So they use IoT devices in cruise ships a lot. And then there is this USAID project for SCADA and cyber physical system security training. This was for Ukraine, actually. It's freeze. So we were basically training professors in Ukraine on cyber physical system security. And then there is a project on NS3. We have a deep interest on NS3 at University of Washington. So more information about my websites and lab sites and Google site. So if you would like to check further information and if you would like to talk further, it's my email. Thank you very much. I finish here. I think, yeah, hopefully any time. Thank you. So I'll be happy to get any questions. I think we have 10 more minutes. Absolutely. Any questions? I know, some of them are fast, so might be broad questions. That's okay.
With the zero RTP idea, this is more a broad question. How do you try and get people to adopt that? Like, in general, is it difficult, or is it something that's kind of immediate?
You mean how to deploy it?
Yeah,
Yeah, it's not difficult. So it's basically you need to, for those devices, you need to just upgrade the firmwares, and it will just work. Yeah. Because they already have TLS. Oh, okay. So you just upgrade. Yeah, this was the question that they asked when I present this to utility companies. The first question they ask is, okay, how can we use it? Like, what is the cost of it? Because typically it takes some investment. And when you say, okay, it's easy, remotely you can configure those, so they're happy.
question about the case study.
Which one?
The one between the energy control center and the electrical customers. So I was wondering how, how does the customer know that the message is indeed coming from the energy control center and not the hacker impersonating the?
Yeah. So that's for these. This SIN, right? It's coming from the IoT device, right? So it initially was sent by the control center. So that's sent by it to every node. So you check those numbers. These are random numbers you generate. So if they match, that means it's coming from that device. So initially you provision it to the field device, and the field device communicates with you with that number. It's like you're giving it a token, and then the field device is saying, hey, here's a token, I would like to talk to you. And then they check the token, oh, okay, yeah, this is matching ours, so fine.
So is it similar to pre-shared keys?
Similar, yes. But it's not a key, in this case, it's just a random nonce, that means random number. Can that be intercepted? Yeah. So this is a hash, right? So you need to, if you hash it, then they don't have access to this. And when you continue doing this each time, you need to get a new hash. So they don't have access to the nonce. Right? So they have access to, they just see the hash, but it doesn't matter.
How does the nonce get there?
How does the nonce get there? So let me see.
Is it over the air or something to the USB?
So here the nonce is generated for each device, and this is sent to the field device.
How is it sent?
So it's sent as a hash, right? Right. It's sent as a hash. Sorry, it's sent as a hash. So you get the hash of it. You store it here as the hash, and then you compare those hashes. Yeah. It could be intercepted, but you don't have that information, right? I mean, initially you have this. I'm sorry, this is I'm sorry, yeah, you're right. So the configuration phase. In the configuration phase, I forgot to mention that the configuration phase is separate from the key generation, right? So we're assuming that in the configuration phase, there is a setup already, and you send these parameters in a secure way in advance. So that's, yeah, so that is done. I forgot to mention that, sorry. That is done, for instance, might be a previously shared key that they can use to encrypt this information, or it might be another way, or it might be, as you said, it's just manually, they share this. And then once it's set up, then the rest is just automatic.
How is it different from sharing the chain of secrecy?
It's similar. The only thing here is that you're keeping the state information with the chain, right? So with this, you are ensuring that you're saving one message or 0.15 message, because otherwise there is, in the pre-shared key approach, that is in TLS 1.3, there is such an approach, but it is not replay attack resistant. It's not protecting against replay attacks. So that's what they say. That's why I mentioned this here, that this is a replay attack resistant zero RTT key exchange. So you can use it similarly with TLS 1.3, but they don't suggest it with critical applications. We looked at the standard. In critical applications like smart grid, they don't suggest it because it's easily can be attacked by replays. So we are with this chain, we are providing that replay attack resistance, and at the same time we are keeping the zero RTT saving communication.
As it is scalable, you have many devices come to.
Yeah, the scalability comes from the message number of messages, right? So in one message, you're sending your data, encrypting it.
No, I mean
So we're
in the configuration.
in the configuration. You mean the setup phase? Yeah. The setup phase is just done once. Yes. I mean, we don't measure the.
Time once, but if you have 2,000 devices, it's going to be very tedious once.
Well, you need to do that, right? I mean, once you do it, you set up for 1 year or 2 years, then it will continue to work.
I guess the question is, does it have the same values, or is it a one-to-one relation?
Share the same. No, for every device, there's a separate.
That's the same. So are they, at the end, are they identical to each other? Or
You mean the hashes?
yeah.
No. For every device, there's a separate hash. That's why we call them S1, S0, S1, whatever. So it brings a lot of advantage when you have especially data, background data. So in our tests with the actual LoRa, I mean, I showed some results there that's really saving a lot. Yeah, it's simple. The idea is simple, but the results you see here are really very attractive, like here. With the UDPs especially, if you can provide that reliability, that saves a lot. But this guy, I mean, this was the CTO of the utility company, and he was mentioning this as a major issue. So for them, this is a big hassle. So, you know, such a solution would save them a lot of labor. They don't use LoRa. It was a very old. I wouldn't say it's 2G because I think 2G is not deployed anymore. But it's they are using radio communications. Probably it's like something proprietary. But he mentioned us the bandwidth. So we try to mimic it with LoRa because LoRa is very limited as well. So that's the best, I mean, in terms of compared to Zigbee or Bluetooth, they're offering probably higher bandwidths, but LoRa is really low. So that was, I think that was similar. So it served the purpose. And I think they are now going to use LoRa, consider using LoRa in some of the applications because LoRa is widely used now as a standard. Given that now there's no 3G, right, in the US, they started to take down 3G as well. So I would think that it will be either 5G, NB, IoT, or LoRa will be used.
Well, I don't see any other questions, so I think we'll go ahead and take this speaker over time. Thank you very much.
Thank you.